So the game I'm playing is this. I've got a group G, finite, or always finite, even if I don't say it, in SLNC, and I can do, this is acting of course on C to the N, and so I can make the quotients C to the N over G, and I can ask for resolutions of singularities. So this is usually called X. And the good case, the case that we're sort of that we like, is when KY is trivial, and this is called a Concurrent resolution. So this is supposed to be a resolution of singularities. So in the old days, these things were called quotient singularities. So nowadays they tend to be called orbifolds, or Delaney-Mumford stacks, if you prefer. And you know, the point of view is really that if you pass to this quotient space, you get a scheme, and you completely forget the group action. And so in the stuff that Johnny Wall's been telling you about, most of the time we're just thinking of the thing as a scheme, as a bare scheme, without sort of suspecting that it has more structure in it. So in this case, when we say orbifold, we really want to remember the cover. And a good case is when this resolution of singularities has got something to do with a group action. Right, so we know a lot when n is 2 or 3. Yes, so Concurrent resolution Y exists. So this is for any finite group in SLNC when n is 2 or 3, the Concurrent resolution exists and is a moduli space. So, I mean, represents a functor. Of G invariant, of G equivariant sheaves on Cn. So in other words, this in this case, this Y is, you know, in some ways you could sort of not even bother to pass to the quotient X. You could think of, I'm going from Cn and I'm constructing a space Y, which is a nice non-singular space. You know, and it has some kind of...
I mean, if it's in S, L, and C, there are no pseudo-reflections, so it's really, you don't need to remember G because it's just... the thing you're saying is that the scheme knows its cover because it's a universal cover of... I completely agree with that. I agree, but nevertheless, we still want to think of this as. So I'll give arguments. I'll give examples of arguments later, where we're working with Y, and the coordinates I use, the objects I use to make the calculations, are not explicitly rational functions on X. They are rationally functions of the orbinates, the orbifold coordinates, the coordinates on Cn. Yes, and you know, it's a difference of point of view. It's not necessarily technically very significant, but we want to think of this as not being, not really. What I meant is that if you have G, L, and C, then you need to
take this step?
I will make this point later when I say something about GLN. This X, under this circumstance, as Fabrizio says, this X knows his covering. So he knows what the covering is. Anyway, I want to get on with the rest of the talk. The main point of the talk is what happens when n is greater than or equal to 4, and and the answer is not much. Or what happens when G is in GL3n. Now I want him to be, for the reason that Fabrizio said, I want this to be a finite group still, and I also want him to be small. In other words, the group, there is no orbifold behavior, there's no fixed points in codimension 1. There are no quasi-reflections. Yes. So I want to say a little bit about this positive statement here, and then I want to find some basically quite minor and rare objects that we can, cases where we can actually study these questions and understand what's going on. Yes. So in particular I want to say this, that so some rare cases when we can answer the questions for G in SL n C n greater than 4, and so in other words, where the technology that we have, which is basically the technology of surface singularities, can tell us what it is we're supposed to be doing here. And then I want to do this case G is 1 over R of 1A R minus A. So this notation here means the group is the cyclic group mu R of rth roots of unity, and an element in there, epsilon, acts by xyz goes to epsilon x, epsilon to the a y, epsilon to the minus a z. A and R minus A are the same thing. Yes? So this is important in three folds. This is in this case x is C3 divided by this mu R is the terminal quotient orbifold point. And mainly, the geometry of three folds is sort of basically built on this object. If you only understand this, then you already understand most of the issues in threefold minimal model program.
You can remind people that this was the total space for the QHD smoothing of the cyclic.
So there's a very important point about this, which is this guy here. If I set x equals 0, I get a third of a minus a, which up to choosing a different primitive root of unity is the same as 1r of 1 minus 1. And this was one of the guys that was in practically all of Johnny Wald's talks. This is the cyclic quotient, the singularity, the singularity, hypersurface singularity theory, that the singularity theorists call a r minus 1. So you really want to think this as a one-parameter smoothing of this guy, but with a sort of equivariant, not completely trivial deformation direction.
So it's a one parameter smoothing of the r squared RA minus 1.
Yes.
That's the total space. So the function xz.
So look, you got to give 4 talks, and I'm only giving 1 talk.
It's yz plus x to the r.
Yeah, yz minus x the r is the function on there, and then specify
of course, I'm not. I'm not against what you're saying. So in this case, so the work I'm talking about here is ideas of originally Danilov. Lots of people have contributed to this, but especially Oskar Kędzierski. Who wrote his thesis about 5 years ago, and my Korean student Jung Sung-jo, who's due to write his thesis later this year. So in this case there is a preferred resolution, and the question is whether or not this resolution represents some sensible functor. Anyway, I'll come to this. And so, you know, I'm certainly not pretending that there's any answer here for SL4C. I'm saying that there are some, basically, cases that are very thin on the ground, but where you can say something. So, what do I mean that a lot, we know a lot? So so in the case n equals 2 or 3, the y, or one of the choices for y is the G Hilb of C3. So this is so let me sort of get around to defining what this is. This is so I say that a G cluster is a subscheme Z in Cn which is finite, zero-dimensional scheme, which is G invariant, which is of length of Z is the order of G, and with the property that if I look at the functions on Z, this is the regular representation of G. This is C of G, regular representation. Yes, so the case to obviously the first important case to bear in mind is I've got, if I take a point here P, which is nothing to do with the fixed points of the group action, and then I take the orbit of the I take G times P, I get a free orbit, and that is one of these guys, right? The number of points here is the order of G, and the functions on it is a set of points in one-to-one correspondence with the group. So it's a set of numbers in one-to-one correspondence with the group, and the group is acting on it by just permuting the points according to its action on itself. So that's the regular representation, right? And then the interesting thing happens when you know, some of these points head in towards a fixed point of the group action, and then what I'm doing here is I'm allowing the fibre, the orbit here, not to be a set, but to be a scheme, a subscheme, an unreduced subscheme, and then it has extra structure and so on, and maybe that tells us what to do, right? And so G Hilb of Cn is it's the fine moduli space parametrizing G clusters. Yeah. So in other words, just to spend a little bit of time on this, I can write IZ contained in the polynomial ring x1 up to xn. This is usually xyz. So this is the functions that vanish on z, the ideal of z. This is mapping down to h0 of oz. Yeah, so knowing the subscheme z, knowing the functions that vanish on it, affine scheme functions is one and the same thing. Right, and you know this guy if you know him in degree up to, you know, the order of g or twice the order of g or some number, some bounded number. And so this Hilbert scheme is a closed subscheme of the Grassmannian of codimension G subspaces in a space of polynomial rings. So this is a very simple construction. You don't need too much Grothendieck foundations to be able to define this properly. This is a very simple structure. So let me give an example straight away, because I need this later, especially I need this for this case. So if I look at the group 1 over R1 minus 1, yes, so this is C2, and I've got that group, the group action written up there, right? And so let me write U and V for coordinates here. They're orbinates on C2 over G. This is x, y, z with xz equals y to the r. So if I write, I'm going to write 1 u squared u to the power of r minus I minus 1, and then I don't write the next one, and then v squared v, I'm sorry, this is I minus 1, v to the power of r minus I, and I don't write the next one, yes, and I don't write uv, right? Then I have the thing I've written down there is a set of r monomials in u and v that contain each of the representations of this group. So this is the group mu r, remember, and the representations of this is the dual group, which is the group z mod r, and by having 0, 1, 2 up to I minus 1, and then I down to r minus 1, I have all the representations of the group. Right, now these guys here at the end are the relations defining the ideal IZ. So I'm going to write u to the I equals lambda times v to the r minus I. In other words, this last guy at the end here is written just as a multiple of this guy, right? And then v to the r minus I plus 1 is mu times u to the I minus 1, and uv equals lambda mu. So if I write this, I write down enough equations here so that modulo these equations, these guys here form a monomial basis. Right, so this is exactly a cluster. This is exactly a G cluster. Right, this defines Z, defines the subscheme, and modulo these equations. These guys here are a basis, and this is isomorphic to the regular representation of the group. Right, and the thing I'm writing down is, so you've seen this picture earlier in the week. The thing I'm writing down here is there's a little affine piece of the resolution with parameters lambda and mu, And so here I'm, this lambda here, this curve here is EI, the ith curve along in the resolution of singularities, and this is P1. It's P1 written as P1 of the ratio u to the I to v to the r minus I. Yes, and so I mean, my point here is, and that's the point that was happening here. This y here is constructed not out of rational functions on x, but it's constructed out of equivariant functions, ratios of functions in the same eigenspace of the group action. Right, so this ratio here is the functions along that curve. And so, you know, the curves that jump out of this singularity, there are r minus 1 of the curves, and they correspond one-to-one to the irreducible representations of the group. Non-trivial irreducible representation of the group. So that's the McKay correspondence. So in this case, I have irreducible curves. EI exceptional over C2 mod G correspond one-to-one with the irreducible representations of G. So more generally, there's this. So this the idea that. So you know what? If you've seen this idea, then you know the idea that instead of taking the set of orbits, you should take the scheme theoretic orbits. Right, and so you think of this thing here as being a scheme theoretic orbit of the group, and this as being the space of scheme theoretic orbits. And it's sort of natural to think, aha, we've got the resolution of singularities in general. So Nakamura proposed this as a way of constructing Crepin resolutions in the case n equals 3. And so it works beautifully in the case n equals 3, and we'll then see that it doesn't work in many other cases. So Nakamura and then, you know, lots and lots of people worked on this, but in particular Bridger and King and Reid have this result that for n equals 2 or 3, a G-Hilb. So setting y equals G-Hilb of Cn is a Crepin resolution of x C2 mod. So the morphism that goes from there to there is a Hilbert-Chow morphism in the moduli theory of in Mumford's terms. And so this means you think of this space as being the space where a jumping condition of codimension in codimension 1 takes place. So Chow, instead of having Hilbert scheme where you think of a space of polynomials defining some object, here you say there's a codimension 1 jumping condition where they fail. So the points touching together is a codimension 1 condition. So so there's a morphism from here to here, which is what's called the Hilbert-Chow morphism.
So in this case, G-Hilb is irreducible, or Cn? So G-Hilb is irreducible in this case?
It is. Look, I just said it's a Crepin resolution. When n is 2 or 3, this is a perfect construction. In particular, it's irreducible, but it's non-singular. It's local Calabi-Yau manifold. Right? When n is 4, absolutely none of that holds. In particular, it doesn't have to be irreducible or equidimensional. Okay, and then there's this result that you know, I have C3 with the Cn with the group action, and I have this x and I have this y, and then we have the result that that the derived category of y and the derived category of G equivariant Cn are you know, equivalents of categories. You're not allowed to write equals. So this means the bounded derived category of coherent sheaves on the resolution y is the same thing on Cn. And so, you know, that's sort of at least foreshadowed in that result here, right? So there's a derived equivalence of categories here. And you know, it's a sort of surprise or perhaps a shock to me to see that in this case the language of derived categories is actually much simpler than the corresponding language in ordinary homology or cohomology theory. This was, you know, I mean, Verdier and Gonzalez-Springberg had a result which was more or less the same result in the case n equals 2 already 100 years ago. Yeah, so that's what we know. That's what we know and what's good in the case n equals 3. So later on I'll say a few words about this is a particular case of representations of the McKay quiver. I hope I'll remain coherent enough to define this later. Particular case of representations with stability. And so if I take representations of the McKay quiver with a different choice of stability conditions but still generic, then I get different Crepant resolutions. That includes the case n equals 2, where there's only one Crepant resolution of singularities. The unique, the resolution of singularities, if you think of it just as a scheme, is unique in the case of surface singularities. This is just the minimal resolution of singularities. However, this one and the same space here represents sort of over there r factorial different moduli problems, right? So in the threefold case, the result is that for every generic stability condition, I hope I'll have time to explain this later, for every generic stability condition, the BKR result proves that the corresponding moduli space, so this will be called M theta, is a Crepant resolution, and every Crepant projective resolution is obtained in this way. So, you know, these are very beautiful and you know, very nice results, and it's you know, going to be deeply dissatisfying to everybody that nothing like this happens in higher dimensions. So let me deal with this case of so let me consider G in SL NC. So I'm thinking here that n is greater than or equal to 4, and so what I want this group to be, I want him to be diagonal. So this means he's a diagonal subgroup of a subgroup contained in the maximal torus of this group, and I want so for simplicity, let me just say he is 1 over r of A, B, 1, 1, n minus 2 copies there. Yes, and I want A plus B plus the number of these is r. Yes, and so, you know, what I'm doing here is I'm saying, well, So when I do the quotients, here I've got Cn, I'm doing the quotient by, this is a cyclic group, this is the group mu r. It could be a group with 2 generators, but I want that all of these coordinates are congruent modulo the integers, right? And so when I go down to Cn divided by G, this is a toric variety. And the question about a Crepin resolution is a toric question. And I'm going to tell you when there exists a Crepin resolution. And the answer is very simple and very striking. So let C be the inverse of A mod R. So we do this all the time. We, you know, this is so when I do AC, this is congruent to 1 mod R. Right. So here I'm doing 1, and then the some number D that turns up here, and then the C, like this. Then a Crepin resolution exists if and only if and only if these numbers add up to R rather than some multiple of R, right? So this means that C times n minus 2 plus 1 plus D is equal to R. Or in other words, it means that C is less than R over n minus 2, not minus 1. Yes? And this is the very beautiful thing, and when I do R divided by D, so D's that guy, this is a continued fraction, alpha 1, alpha 2, alpha k. So this is exactly the same notation as other speakers heretofore have used, 1 over alpha 1, alpha 2 minus. So there are two conditions here. One is that C should be small, and the second one is that every alpha I, these are integers, this is a rational number expressed as a continued fraction in the usual way, every alpha I is congruent to 2 modulo n minus 2. Yeah. So look, I'm saying it as if it's some kind of gobbledygook. I'm going to explain why I make this assumption and what this result means. It's really very, very simple. So, quite generally, in this sort of context of toric geometry, I write down L for the lattice. So if G is diagonal in SLN, I write L for the lattice Zn plus 1 over R of A1 up to AN, and this is for all G in G. Right. So these guys here are contained in the maximal torus of SLN, so they're diagonal roots of unity, and for each one I can write him like this. So I write plus Z times this. So this is an overlattice of Zn of index some of R's, some product of R's. Yeah, depending on how many generators a group G needs. Right, and a Crepin resolution is, so let me draw the picture as if it's 3-dimensional, but you have to imagine that this is n-dimensional. So the thing I'm drawing here is the coordinate system in Rn corresponding to this Zn, right? And so this, modulo the integers. This is the units cube here. So this is the E1, E2, E3, dot, 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 En. Yes? So this is just the unit, this is the front cone, the, what do you call it? The positive octant. And this is the units cube in there. So this lattice, every point of this lattice, modulo the z to the n, is somewhere in this cube. Right? And so it's traditional to draw this picture here. So here is the n-1 simplex based by E1, E2 up to En. Right, so this is called the junior simplex. So every point in this lattice is somewhere in this cube, modulo z to the n, and either they're on this plane, or they're on this top plane, or there's the zero, which is down here, and then or they're somewhere in between here. Right. So if we're this guy here is an integer modulo. This guy here is an integer because I'm in SLN. Right. So Kreppmann resolution is a basic subdivision of the front octant with one skeleton consisting only of junior vectors. Yeah, and so what I'm supposed to do is, if possible, choose some points in there, make little simplexes, simplicial cones that are basic, that are spanned by a basis of the lattice L, and use that to build these copies of Cn that will make up the so Kreppmann resolution Y is this. So I have to take, so this picture's sort of pretty awkward to look at. Let's draw him bigger, like this. Right, so I'm going to draw him E1, E2, and then E1 up to En. Right, I'll introduce special notation for this. Right, what I'm supposed to do is somehow or other triangulate this. So you know, write down triangles here that are basic, meaning they're one skeleton, meaning the vertices of the triangulation are form a basis of this lattice L. So that's to give you something non-singular, and then if I want to find a morphism, a proper birational morphism, which is a resolution of singularities, I need to do this whole of this triangle. Right, now you notice what I've done here. I've chosen, I'm doing something special with E1 and E2, but all the coordinates, all the last n-2 coordinates are congruent modulo the integers, right? And that means that if there are any junior points at all, they're contained in this triangle, in this two-dimensional triangle, where this point here is A primed, which is 1 over n-2 of 0, 0, 1, 1, 1. Yeah, so if I take points on this plane, then all of their coordinates are multiples of that 1, 1, 1, 1, 1 thing, and so they're all congruent modulo R, but they're also less than R, and so therefore they're all equal, right? And the conditions I'm writing down here is just the conditions to have a proper link of this vertex, right? This vertex here is not a lattice point, it's failing to be a lattice point by this denominator, and the conditions I've written down here are just enough to determine that there are lattice points of the lattice L here, so that I can, so when I'm here, I'm joining this up to the n-1 simplex, whereas when I'm down here, I'm joining these up separately to n-2, n-3 simplexes, or something like that. Yeah. Anyway, that's the results. But the really nice thing about this is and. So I've told you the necessary and sufficient condition for equivalent resolution to exist, and it is this mumbo jumbo with continued fractions. So this is also a continued fraction calculation. If you want to know who C is, you run the Euclidean algorithm. Yes, and in this case, G Hilb of Cn provides good choices for equivalent resolutions. Yes. So, in other words, there's a game here which tells us exactly how to fill in this this triangle. So I run continued fraction algorithms at each of the three corners, including this one. So, including at this corner, I'm doing something a little bit funny, but with these conditions here, these conditions ensure that I can do all of this remaining within this junior triangle. This is this picture. This here was a n-1 simplex. This is a triangle, a plane triangle. Yes. I should say this is a result. This was in the thesis of Sarah Davis, and it's a joint paper with Timothy Logvinenko. And I think it's a well-known principle that the more authors a paper has, the slower it is to appear. So the new feature here is called trap. So I'm going to draw a trap. So I'm drawing it just in the case of so it looks like this. So I'm drawing the overlattice L. I'm drawing case n equals 4. This point here is half of E3 plus E4. This is E1, E2. Right, and the thing I'm drawing is A help, G help is this discrepant triangulation, discrepant basic triangulation. Right, and so he looks like this. Right, the group is the group ZR plus ZR. So R is odd. Anyway. Right, so the picture I'm drawing here is, this is a triangle for a group like this with a regular tessellation, right? And the same, so ditto, the same thing happens here, but in the middle here, G Hilb is doing something which is discrepant. Right, so these lattice points here are not junior. They're the sums of two juniors in two different ways. Right, so if you're a human being, and some of the people in the audience probably are, then you can easily see how to make a equivalent resolution. Namely, you just choose, right, you say, well, I'm left-handed, I'm right-handed, I'm going to do that. Right, that's equivalent resolution. There are two different choices. Trap, this stands for regular trapezium. Trapezium. Anyway, the point I'm making here is this is the class of groups for this work, for which this works, is extremely rare. This is an extremely small subset of all possible diagonal groups. I'm putting myself in the position where two-dimensional pictures will answer all the questions, and even then the answer to the questions is sort of, peculiar and strange, rare. I mean, this can, this condition happens with probability n minus 2 to the power of 1 over n minus 2 to the power of k. So it never happens. It should be very rare. Okay. Anyway, that was. This is one little point. So in this case, you can calculate G-Hilb in this case, or we can calculate G-Hilb in this case, and it is this thing which is very near to being increment resolution, except that it has unnecessarily blown up these points. And what I should have done, instead of blowing up these points, I should have made one of the two small resolutions, one of the two things connected by the Atiyah flop. Yes. So let me go on to the other little narrative. I started up as 4. Okay, so let me look at this 1 over R1A R minus A. Right. So in this case, if I draw this same unit cube, then if I were trying to make, so every lattice point here is congruent to AI R minus AI. So every point in the lattice L, so L is this Z cubed plus Z times him. Every point in this lattice is congruent to one of these guys. And so how many of these guys lie on the junior plane? Absolutely none of them. That's why this is terminal. So there are lattice points here, and they lie here. They all lie on this median plane here, with the last two coordinates equal. So this is y plus z equals 1. And so again, I don't want to keep drawing these on this sort of plane that's slanting away from me. I want to draw it as a plane here. Yeah, and so what happens here is I'm supposed to draw here, because of this condition here, the thing I'm going to do is I'm going to write E3, E2, and then the other lattice points are, for example, here 1 over R of 1A R minus A. And I'm just going to suppress this. I'm going to suppress this last one. I'm not going to bother to write him. Yeah? And so by doing this, I get a picture that looks sort of, that looks something like this. Right? There is, in this picture here, there is one point with x coordinate I over R for each value of I from 1 up to R minus 1. So that's the lattice points in this front cube. Yes? So there is an operation, there's a kind of obvious operation here, which is to subdivide there. So E1 is not actually on this plane, but you can think of E1 as being a point at infinity. So if I'm standing on this plane looking upwards, I'm looking in the direction of the E1 axis. So I can think of the E1 as being points to infinity. Right? And so if you do this operation here is a barycentric subdivision of a cone at some interior point, and it's the weighted blow up of 1 over r 1a r minus a with weights 1a r minus a. So I use the same weights to make a weighted blow-up, and then that's just that barycentric subdivision. When I do this, what I get here is 1 over a of, I'm probably going to get it wrong, I think 1 r minus r. And so, you know, the issue is which order you write these two in, and it's sort of important for various things. Right, and here I've got 1 over r minus a of, so it's the same r minus a, but I can write that as a minus a. Yes, and then I can sort of just think of this as a problem in its own. So this operation here, this weighted blow-up, is called the Kawamata blow-up. So if I do this recursively, I just continue doing this until the thing is, eventually each of these things turns into the simplest possible thing, and that's now, so you know, I'm going to tend to get pictures like this. And I'll draw one or two realistically later. Right, so this picture is called the Danielov resolution. Right, it was written down before, you know, when threefolds were just beginning to get going. It's, you know, the significance of this thing here, the terminal threefold singularity, was also significant in combinatorics before minimal model programs started. Right, but Danielov wrote down this picture here as a preferred resolution of singularities. So it's not a Crepant resolution. Each of the divisors that come out of these blow-ups has discrepancy 1 over r, 2 over r, 3 over r, up to r minus 1 over r. Right. So, and you know, this is an algorithmic procedure. There's a unique way of doing this. A unique sequence. Not the order in which you do it is not unique, but the end result is unique. You do this blow up each time, right? So this is something called the Danielov resolution, and the question is to try and make sense of this in terms of McKay correspondence. So you know, here's a realistic example. If I do it, so I'm doing 1/5 of 1, 2, 3. Realistic but not terribly adventurous. The adventurous ones involve quite a lot of so I'm supposed to write here 2 and then 4 and then so this is the picture. Yes. So you'll notice that this thing has 5, that's R cones involving E1, and that is basically a resolution of the elephant. That's basically what happens if I look at 1 over 5 of 2, 3, which is, as we know, is the same thing as 1/5 of 1, 4. This just means up to isomorphism. Yes, and this has a, you know, so that has this thing. This has 5 affine pieces making up its minimal resolution, right? And there are another 4 of them down here. So this thing has total Betti numbers 2r minus 1. There are however many it was. There are r minus 1 class. There are r classes of curves and r minus 1 classes of. Sorry. There's h0 is 1-dimensional, first Betti number. h2 is r minus 1, and h4 is r minus 1. And so I want to make a kind of. I want to have. So I want to have one description Danielov resolution as a moduli space m theta, and I want a description of his cohomology or derived category of his so let me write d of y. So the Danielov resolution is called y. He's the closest thing we can come to a correspondent resolution. I want describe dy in terms of representations of G. Right, and so far we can't do this, but we're in some ways quite close to it. Yes. So you notice that when I said this, I said I do this blow up, and that breaks the problem up into a half of 111 and a third of 121. Yes, and and then I blow this up again and blow this up again and blow this up again. Each of these, in terms of the derived category, you could think of each of these as giving an exceptional object to the derived category, and this giving us, if I take these in some order, I get a strong exceptional collection, and the complement of that is the complement of the derived category of the quotient singularity x. However, I don't want to take this beautiful object and break him up into exceptional objects. I'm not interested in that. I want to see the whole of this in terms of, preferably, because I have 2r minus 1, I want 2 copies of G of the so the represent in this case, because G is an abelian group, his character group is also an abelian group. So I mean, this is a hope. This isn't a result yet. When people write a paper with towards or beyond in the title, it means it's mostly speculation. I'm sorry? Of course not. So look, I do this y equals Danielov resolution. Then he contains divisors E1, E2, E r minus 1, corresponding to the different steps of the blow-up. Yeah, and ky is the pullback of kx plus 1 over r of E1 plus 2E2 E3. Yes, and so
the discrepant resolution from just looking at this sub-half combinatorial data of the subdivision.
Look, I told you. I mean, this procedure is really very robust. I'm taking the lowest point here. That's the E1, right? The fact that in this picture he's only just above this plane means that he's got very small discrepancy, right? So all of these guys have discrepancy less than 1, right? So in this context, G Hilb, if I write down G Hilb of C3, this is very bad, is no good as a solution. Right, he's no good in 2 different senses. In the first place, he's singular, so he's not a good resolution of singularities. In the second place, he's much too discrepant. Sorry, if I sort of try to draw this, right, I have this picture, right, and the A Hilb always does this, right. In other words, it goes up with the highest slope to some point here. In this case it's only 6, but in general it's some huge number. So some huge discrepant divisor in there. So this is a very bad operation. And this is not a simplicial cone. Right? So this is still singular, but this is, you know, you're working with a functor, and you don't argue with a functor. Right? The functor does what it wants to do, and you know, you can't. So we know how to calculate this. Ali Crow, well, I mean, I computed this in around 1990, 1995. Ali Crow has, I think, a paper on it. Yes? So I want to get to, so Kędzierski proved, Kędzierski's thesis, sorry, give him his cedilla. Kędzierski proved that there exists a theta, so maybe I'll explain this in just a minute, stability condition, so that m theta, this is moduli of representations of the McKay quiver, with stability right, has a component whose normalization equals the Danielov resolution. Yes. And Sundro has proved in particular that you don't need normalization, and I believe, so, you know, in mathematics, when you have an unknown problem, there are always two conjectures. One conjecture is that m theta is irreducible, and the other one is that it's sometimes reducible. And if it's sometimes reducible, then there will be a first case. And we don't know what that first case is, but it's probably quite big. Probably involves, you know, a bigger than 4. So, you know, we know quite a lot about this problem. We don't yet know, you know, this will be settled in the next couple of months. I mean, we do know how to do this. But anyway, Sundro is sort of, we don't need the normalization, and we don't need, whether or not we need the components is, anyway, as I told you when you asked me to give this talk, it would be better to get Sundro to give the talk, because he knows the subject better than I do. So let me just explain what you have to do to get results of this nature. So the McKay quiver. So I take irreducible representations of G. So in this case, G is mu r, and so irreducible representations is elements of Z mod r. Right? And then I link these together by rho I is connected to rho j if rho I tensor the given representation Q, so this is C3 with G acting on him, is some Nij rho j. Yeah, and so you know we know the dual group here, the group of characters of G is this Z mod R, and so it's natural to write him as a polygon. And this Q here is the direct sum of 3 irreducible components, one of which is 1. So this is 0, 1, 2, 3, 4. So there's an arrow coming out of 0, an arrow coming, another, this is multiplication by x, this is multiplication by y, this is multiplication by z. Right, the McKay quiver is that. Right, so it's a quiver with 5 edges, 5 vertices, and 15 edges, 3 coming out of each vertex. Yes? So I'm going to do representations of this quiver. So you know, we're doing toric geometry, so the dimension vector is always going to be 1, 1, 1, 1, 1. Right? So what it means is I put a one-dimensional vector space at each vertex, and then I put a 1 by 1 matrix, otherwise known as just a number, on each of these arrows. Yes, and then I write down the condition that commutation, right? And this is a representation of the McKay quiver, right? So in representation theory, we're interested in representations up to equivalence or isomorphism or equality or whatever it is you want. And that means that at each of these vertices, I multiply by C star. So I have C star to the power of r acting on this thing here, just changing the basis in these vector spaces. And I want to pass to the quotient by this. So passing to the quotient by a group action, as we've heard earlier in the week, is the problem of geometric invariant theory. And if you allow too many of these guys, too many of these matrices to be 0, then you get some pathological thing, like projective space. You have to delete the origin before you divide out by the group action. So we do this several times. So the solution to this is to introduce theta. So theta is a weighting, and then you demand that no subrepresentation should have weight less than 0. Right? So this is exactly the Hilbert-Mumford stability criterion that Radu taught us about earlier in the week, right? And so specifically, if I give 0 the weight minus 4, and each of these 1, 2, 3, 4 the weight plus 1, then the space, the quotient by this is exactly A Hilb, right? Because the condition that no subrepresentation has negative weight means that anything that contains the minus 1 must contain all the others. Yes? And so that's stability. The G Hilb is the particular case of m theta with that obvious weight, right? So in this case, the theta that we're going to choose is, so I'm getting to the place where, oh dear, I'm sorry. So, I'm sorry, I'm going over time, but, so this is, Sungjo says, so let's not worry too much about what happens down here at the bottom. Let's only worry about what happens up there at the top, which is close to the elephant, right? Close to this 1/5 of 1/4, right? And so what we do is we write down So I write down 0, 2, 4, 6, 2, 4, 1, 3, which is y. Yes? And what I'm doing here is I'm saying I am going to nail down this C star action by saying each of these arrows is 1. So by doing that, I've chosen a basis. This is exactly like setting one of the xi equals 1 when you do projective space. Right? And then the next one we're going to do is, I need my notes for this, and I hope somebody will correct me if I'm wrong. So what we do is we're going to cut this here, and we're going to write 1, 3, and then 0, 2, 4. Yes? And that corresponds to passing from this area here to this area there. Yeah? So this is a module over the polynomial rank KXY, which is a regular representation of the group because it has exactly one of these exactly once each. Yes? But on the other hand, it's a module that has two generators. Right? And so the 0 and the 1, when we eventually write down the theta, the 0 and the 1 will have negative values of theta to ensure that this guy here is stable. Right? And then I write down etc. So I don't. So there's right, so I'm writing down, this is 0, 2, 4, 1, 3. So each of these operations consists of taking this picture, cutting him at one point and pasting him back there. Right, that corresponds to the 5 stripes of this resolution near the point E1, near the elephant. Yes? And so now we write down, so theta is defined by the condition that these guys are stable. So specifically it means that theta 3 is greater than 0, and theta 1 plus theta 3 is greater than 0, and theta 4 plus theta 1 plus theta 3 are greater than 0, and theta 4 is greater than 0, and theta 2 plus theta, anything that stands up above the generators here, so that combination there must be positive, because we're not allowed any sub-representation which is negative. So you do that, and then so here at the moment we were determining theta. Then it comes to using theta. So m theta is the space of, so this is a fine moduli space of theta stable clusters, constellations, representations. Yes? And so, there's some kind of computation involved in doing this. So exactly how you determine which of these, so this is called the lacing. I'm taking a quiver, the quiver is just this thing here, and then I'm commanding that some of the arrows in it will be 1 to kill the group action. Yes? And so here I'm writing down 5 lacings corresponding to those 5 stripes. And there are 4 similar ones for the ones under the bar, for the ones under the dogleg picture. Okay, and so the question about whether this is irreducible is exactly the same now as the question about whether the pictures corresponding to the guys under the dogleg are the only theta stable lacings of these pictures. And I believe that this is either true or it's not true. So if it's true, we'll have a proof soon. If it's not true, I'll have a counterexample soon. Okay, sorry I went over time.